everyone. Welcome to the fourth NCI and Intersect showcase, AI and Machine Learning in Astrophysics. My name is Chris Power. I'm a Senior Principal Research Fellow at the International Centre for Radio Astronomy Research at the University of Western Australia. My research tackles dark matter and galaxy formation theory using supercomputer modelling. I will be the moderator for today's showcase. Now, let's welcome Satish Nair, the CEO of Intersect, to make some opening remarks.
Thanks, Chris. Good day, everybody, and a warm welcome to today's showcase. My name is Satish Nair, and I'm the CEO at Intersect, a co-host of today's event. Today's showcase is the fourth in a series of educational sessions that Intersect and NCI are collaborating on to provide further focused education for postgraduate level researchers. The subject of today's showcase is fascinating as we often look up to the sky and wonder at its expanse. It's of particular interest to all those who are keen in learning about the use of AI and ML in understanding the working of the cosmos and unraveling new physics. I would like to thank the speakers for their time in sharing their knowledge, inspiring research, and raising awareness in this field. Also, a special thanks to Mayun from Intersect for her work in organizing this event. I'll not take any more time and hand over the chair of today's showcase, Professor Chris Power.
Thank you, Satish, for the opening remarks. In the showcase today, we are very fortunate to have four excellent speakers, internationally recognized for their leadership in AI and machine learning in astrophysics. So now it's time for me to introduce our third speaker, Yuan-Sen Ting. Yuan-Sen holds an associate professor appointment at both the Australian National University and also Ohio State University. His work is at the nexus of machine learning and large astronomical surveys, extending Bayesian statistics with deep learning methodologies. So over to you, Yuan-Sen.
Okay, thank you very much. Let me share my screen and do the full screen. I presume you can see my screen?
Yes.
Okay, great. Okay, and thank you, Chris, and good morning, everybody. I really love to give a remote talk because I can wear my jacket and Lululemon at the same time. But anyway, so as Ashley say, I will be mostly focusing on large language models. So Ashley did at a good point. I will just continue to talk about what I think about large language models and why I think it's quite a game changer of how we do astronomy. So let me start by talking about why we are all here. So obviously there are lots of interest in AI for science. So for example, in the US, the NSF has awarded about $200 million for AI research, and half of them is actually dedicated for science, right? So if you count the biological sciences, the physical sciences, and the environmental sciences. The question that, of course, we are all here to discuss is whether or not this is a hype, a myth, or a real deal. And so, of course, there's reason why people are so excited about AI for science. I think a big part of that play a big role is the AlphaFold, right? So people say since the AlphaFold has totally transformed how we do life sciences, we should expect to see that for the other field of sciences. And because of that, right, so quite often I got asked the question from non-astronomer and in AI about why there is no AlphaFold a moment yet in astronomy. So of course we have, I didn't plan for this, but of course we have heard from the first talk that like a lot of the effort in AI for science are focusing on two regimes, right? So on the one hand, we are extending how we do a statistic, and including I myself has been working on that, in particular in cosmology, and try to understand the state of the universe. And the other regime is what Ashley talked about, because there are more and more data that are coming online. So of course you need a very efficient broker or classifier to find the anomalies. And all of these are super important, you know, and I have been working on that. But would argue that like none of this is really at the level of the AlphaFold, right? So this will improve how we do science, but it would not fundamentally change like astronomy, like not at the level that the humans still need to be involved. And the thing that I want to talk about today, I will start by this famous like article called the Beta Lessons from Rich Sutton. So what Rich Sutton mentioned is that in the regime where we have a system that can scale up to arbitrary complexity, the right way to think about the question is try to understand how we can let the agent to discover like we can, instead of we like instructing them to discover as we want. So I think like this is a important part that we need to like distinguish, because like a lot of things that we have been doing in AI for astronomy has been focusing as you're using AI as the tool. So we are instructing how the AI should do the discover as we want it to be, instead of letting the AI to help us, to instruct us to do science. So with that, so these are the three things that I want to discuss with you today. So one is where we are at in AI for astronomy. How do we quantify that? What is the problem? So I think I mentioned a little bit of the problem like in the last few minutes. And I want to talk about what I feel could be a AlphaFold moment for astronomy, right? So I still think a lot of things that we're doing are amazing, but we also need to have some blue sky research that will change how we do science. And of course, I will talk about how we can get them more efficiently. So let's talk about where we are at in terms of AI for astronomy. And in particular, how do we sense the growth of AI for astronomy? So there is a lot of interest in AI for astronomy, but how do we quantify that? How do we know if AI is really helping us to do science? And how do we understand that interaction? So this is the thing that I got quite excited about in the last few months, mainly to understand the knowledge graph in astronomy. So what is showing you here is a knowledge graph that we constructed with Microsoft. So what we try to do here is try to go through all the literature in astronomy and try to understand what are the concepts that appear in astronomy. So in this case, this knowledge graph has about 25,000 concepts, and we try to understand how these concepts interact with each other, and from which we can start to understand how to quantify the influence of AI. So of course, I will tell you how we get there, so that just to show you the knowledge graph first. But let's talk about how do we really quantify that, right? So how do we construct the knowledge graph? The first thing that we do, of course, is try to expand how we visualize the field, right? So like a lot of things that we have been doing in astronomy, quite often we are relying on keywords. So if you write a paper, you have to select the keywords from this 1,400 words that we call UAT, the Unified Astronomy Thesaurus. But A, like that is too limiting, it's too granular. But B is also like a bit like outdated, right? So if you, in order to keep up to date, like what would be the new concept to appear, it's very hard to do that with the UAT, because that has been set even you get like updated every few years, it's still too late. So what we end up doing is to use large language models to extract all the concepts in the paper. So no one can read all the paper, but large language models can. So this is nice. So let's start by talking about the basic thing, right? So let's see how the concept has changed over time. So how much the concept has grown over time. So what is showing you here are the number of concepts in thousands as a function of years. So if you're just focusing on the concepts that are related to science, then it grows from about 7,000 to about 11,000. So that's quite healthy. So the number of concepts in the last 50 years have grown by like 50%. You can also look at the concepts that are related to a numerical simulation. So Salman talk about that, as well as the statistic. And this is also quite healthy, right? So the number of concepts that are like related to the simulations grow from about 1,000 to about 1,500. But the same cannot be said for machine learning, right? So if you just count in the literature how many of concept has new concept has appeared, it has grown from like 150 to about 230. And this point to a problem, meaning that there is a lot of hype about like applying like machine learning to astronomy, but a lot of things that we are doing, of course, are still like, relying on somewhat older methods. But we can also like further like quantify, right? So I, like as I mentioned earlier, the goal here is try to understand how these different type of concepts are interacting with each other and how they inspire the growth of science. And this is something that we try to quantify like better. So in particular, we try to understand the distances between the concepts as a function of years. But how do you understand the distances of concepts? So what we did here is try to use a literature a citation metric, just try to understand how the community is viewing the different concepts. So let's say I want to understand the concepts between dark matter and plasmon. What I would do is to find the paper that contain the concepts dark matter. I will look up for all the papers that either cite this particular paper or reference this paper. So you can count the number of paper that this paper cite that contain the other concepts. So this, of course, is a one distance, meaning that if I want to understand plasmon by already knowing dark matter, I just need to read two papers, right? So I need to read, like this paper in red. But if I also read the paper that cite this paper, I will lead to the other concepts. But you can imagine there are many concepts that are further away, so you cannot directly reach them with one distance. So if you grow the sphere, then the number, the denominator will grow. So how we define the distances between the concepts here are just saying that like in terms of a probability, how likely you will encounter a new concept B by reading all the papers that is related to A. But that's just the technicality. But like with that, you can start to see how these two different type of concepts are interacting with each other. So what is showing you here, the y-axis are the average distances between the concepts that are from the numerical simulation with the concept that are from science. And for this technical and scientific interaction, you often see this two-phase evolution. So what are we seeing here? So let's focus on this phase, right? So if you look at this phase, you will see the concepts that are related to the numerical simulation are decoupling from science. And this is what we call the technology development. So the way to think about this is that like around 2000 to 2005, there are lots of people who are like developing n-body solver. So they are interested in the technology. So they are developing quite a lot of new techniques, but they are not necessarily applying that to science, right? So, and this is why you see the linkage decouple. But after a 5-year like evolution, then people will start to deploy the new techniques, meaning that now people are using the concepts that has been developed in a numerical simulation and try to run n-body simulation. Right? So this is why the linkage increases. And similarly, you can see the next 5 years, if people are familiar with the evolution of the numerical simulation, this is also the time where the hydrodynamic simulation are becoming more and more popular. There are more technologies that are bringing in these new techniques. And then this leads to like another boom of sciences. This is very healthy, right? You have this two-phase evolution. The way for astronomers, like the way that you can think about this is like dwarf galaxy star formation. So you accrete some gas, and then this leads to starburst, and then you accrete more gas, and then this leads to a starburst. But the same thing is not the same for machine learning for science, and this is somewhat concerning because you can see that there are lots of interest in machine learning and astronomy, but there are really not many accretion of new techniques. And I do see that to be a problem because this meaning that like a lot of these cross citation that we see are still like relying on older like techniques that has been brought in like around 2010 to 2015. And of course, the problem here is that machine learning is a very fast-paced field. So if you are not like actively creating more and more new ideas, then they would drive out the technologies in astronomy. So that's one of the way to think about like astronomy and AI. I think there are lots of like interest, which is great, but also see there are some problems because we quite often are not like distinguishing people who are applying the technique to science, which is great, but also to reward like people who think about the technology, right? But there's also a bigger problem than just the slow accretion of new techniques. And this leads to the question that I posted, that I was like posted like many times, which is, where is the AlphaFold thing, right? So what is the one thing that the AI will change astronomy? And I think that question like itself is quite posted because astronomy is not a biology. What do I mean by that? So if you think about for most of the analysis that we try to do, it often goes as I have some data and I want to test a theory, right? And then we analyze the data to decide if the theory is true or false. And for biology, like this is particularly like important because in the past, when you have no way to predict the folding of the proteins, then you do not have a way, even for that one task, like you have no way to prove or disprove your theory. And this is why when AlphaFold happens, it gives you a pipeline, which leads to a breakthrough, right? Because for this particular like downstream task, biology is a bottleneck by this one task. But for astronomy, like this is quite different because like astronomers are smart. So we kind of know a lot of things already, right? So like that's just a joke, like meaning that, you know, like astronomy, like in many ways is a simpler than a biology. So in a vast field that we already have a pretty successful pipeline. It's not like we cannot do without, right? So this is why if you think about the application of AI to astronomy, quite often say in cosmology, it would improve 10 to 20%, but it will not change drastically. Like it's not as drastic as AlphaFold. So it's not that it's not important, it's just that it will not have the impact. So if you're asking an AlphaFold a moment to convince the senator, I think like most of the things that we are doing are not at that scale, and it will not lead to that scale that we have this like a blue sky type of research. So what could be a AlphaFold moment for astronomy? And this is a thing that I've been thinking quite a little bit, as Ashley mentioned. One of the excitement here is building toward a AI astronomer, meaning that we try to automate the research completely. But let me dissect a little bit, right? So how should you think about this question? So if we have like established that individual downstream tasks is not a bottleneck, then you should take a step back and talk about what the human is doing now. So in astronomy, like most of the time, we are not bottlenecked by a single task, but the role of the human quite often is try to evaluate the state of the research, right? Meaning that, say, for example, a supervisor will look at the PhD student and decide, you know, if the this direction is good or bad, and like propose new theory or new data. Like new data meaning that you can like propose a new telescope, new wavelength, and a new way to collect the data. So humans are often taking the role of an outsider, right? So we evaluate the state of the research and propose the new action. And in a way, that this is very, very similar to playing Go chess. So one way to think about like research is that we are essentially doing a reinforcement learning. We are playing a chess game, like just that the chess game is the research. So by playing more and more like chess game, a more experienced researcher will get more experience and know how to propose by evaluating the states and know how to propose a new theory. So perhaps one way to think about how we can automate the research is to do the reinforcement learning. But there is a problem here because what we call the state of the research is more fuzzy than a chessboard, right? So the human can understand, a very experienced researcher can understand the state of the research, but this is not that trivial for and this is not something that we can like define this as a mathematical reward, because this is all quite implicit, and this leads to a lot of bad taste about AI. Like if people like don't understand like AI, people always say, well, you know, like even with AI, we are still relying, like at least for astronomy, we are still relying on the human intuition or experience, like what like actually like talk about like using the human to upward or downwards stuff, because those come from years of experience and it's hard to mathematically quantify that. The question is, can we actually do that, right? Can we mathematically quantify the intuition? The answer is yes. So you can still do this type of reinforcement or learning, like a policy learning without a reward or function. And the trick here is using the LLM as the rewards. So the LLM, the large language models, implicitly have some intelligence, and hopefully those LLM is strong enough that you can use them as a reward function. So this of course sounds like a bit meta and high level. Let's talk about a specific case that we thought about and we have written about. So let's talk about this simple case where you are feeding a SED of a galaxy. So the SED stands for the spectral energy distribution. So you're looking at the flux of the galaxy at a different wavelength. So the data point here are the data point from James Webb. So let's say you collect some data from James Webb and you feed a physical models, right? So you have some baseline models. You ask your grad student to feed that. And then your grad student will run to you and say, hey, you know, I feed the base models, but I see some discrepancy. So let's talk about what a human would do here. So if you are an experienced researcher, what you would say is that, hey, you know, maybe you should see that the discrepancy have a wavelength dependency, meaning that it's estimated in the optical, overestimated in the infrared. So this might mean that maybe your dust models are wrong. So you should swap out the dust models in your physical models. Or the other hypothesis will be, well, you know, you are estimating the ultraviolet flux. And we also know that young stellar population can create the ultraviolet flux. So what could be wrong could be your models are wrong. This is why you need to swap out, find another GitHub that have a different parameterization. And even with this simple example, you can start to see some of the problems, right? Which is like lots of things that the human do are not mathematically differentiable. And it's not only optimizing the chi-square of the fit. Like lots of this is human intuition and human experience. The question is, can LLM learn through experience, right? And that's the question that we try to pose. So we have this program that we call Mephisto. Why is a Mephisto? Because Mephisto is this a demon that exchanges soul for knowledge, right? So the same thing here, we are exchanging our soul to the AI overlord and try to exchange for knowledge. So how does that work, right? So essentially it's what we call the agentic research. So we are using a collaboration of different agents and see how well you can do the science. So in particular, in this case, we have different agents. This is, of course, a very romanticized way to look at things. In practice, this is what happened. You have many copies of Mr. Smith, and they are all like GPT-4, right? So you try to say, can I really use the GPT-4 and give very specific tasks to different copy of a GPT-4 with fine-tuning, with a retrieval augmented generation, so that you can do the science and learn from the exploration. So in particular, we are using a particular case that we use the data from James Webb, which is quite exciting because people have been looking for high redshift galaxy from James Webb, the earliest galaxy that we can find. You can also define, you also need to define a playground. So we ended up defining the playground using this code called Seagull. But Seagull is not just one code, right? So Seagull is a collection of codes that with different physical models, meaning that you have different building blocks, and the LLM need to learn how to play with the building blocks. So this become a very concrete chess game. And the closest analog that you should think about, keep referring to, is essentially alpha 0. So you let them to play the games, and hopefully by playing enough games, you will learn how to play the chess well. So just that now the chess become feeding the SED. So how does that work? So as I mentioned, you can start with a baseline feed. You have some data, you have some baseline feed, like this is your current state of the chessboard. And then Mr. Smith, number 1, will comes in, and this particular agent is tasked to propose action, meaning that this board has all this information like what actually has for a chatbot. So you have a lot of contact-based information, and it's very good at proposing actions. So you propose a bunch of actions, so let's say 1, 2, 3, 4, and then you have another agents, Mr. Smith number 1, and what Mr. Smith is tasked to do is to write the codes, right? So it will use based on what has been proposed by the action. It will write the configuration file, run the codes. So if the codes do not run, then it would debug the codes. So you write the codes, and then you would generate new fits. And then you have the other two agents. One is to look at the plot, right? So you have these two new results, just like you play the chess, you play 2 different moves. And then you have this board that will learn how to summarize the experience. So this is state evaluation. But this is also quite implicit. It's more than just optimizing the chi-square. You are using the LLM as a agent, and hopefully it can understand why something is better than the other without really relying on a single error metric. Of course, all the LLM are limited by the context of Windows, so you have another agent that do the distillation. So after you have done that, it will store your knowledge, right? So this is more than just prompting the LLM, because you are really let the LLM to explore the data and store the knowledge. So how does the knowledge looks like? So this is one of the example of the learn knowledge. So after by playing the games, so the LLM will learn that now if the fit is over estimated in UV or optical, I have learned that maybe changing this particular parameter, EB minus V, which is the parameter of the dust, it might help to improve the models. So this is the type of knowledge that is not implicit to say GPT-4, because you would not know how to run the Seagull code implicitly, but letting them using them as an agent to interact with the real world data, you will start to summarize some of the knowledge. And does that work, right? So this is of course still very conceptual. And actually it works. So what we have shown here, that we have this paper that we just submitted. So you're looking at how good the fit improve as a function of the learning iteration. So you can think about the x-axis here is how much chess game you have played. So how much SED you have fed it. So you can see that as you play more and more chess game, you fill up the knowledge base more and more. And this leads to a better fit that is significantly better than just a native LLM. So because the native LLM is just a LLM without the knowledge. But here we are also not hard coding the knowledge. So we are just letting the LLM to interact with the James Webb data and using the inherent intelligence of the model to learn about that. And it's even more interesting that you can see like there's a plateau here. So you can see that when you first do the learning, the chi-square is not improving. Why this is the case? So you can plot like the other metrics. So the blue line here show you how many band is well fitted by the models, meaning that within the SED, the different wavelength, how many wavelength are well fitted by the physical models. So you can see that as you first play the chess game, just like playing the AlphaZero, you first learn the policy in a network. So this is also what is happening in LLM. So the first few knowledge that you get is sort of what we call exploration. So you are learning the obvious. So you say, if I see there is an overestimated in the ultraviolet, I will change the star formation history. If I see there is a under estimation in the mid infrared, I will change the AGN. So these are sort of like rule of thumbs. You will improve the number of wavelength that being fitted, not necessarily improving the chi-square. But after you have learned the basic knowledge, so you kind of know what is the rough region of the models, then the model will start to do the exploitation, right? And this is also what we see in this, letting the LLM to interact with the James Webb data. So the point here is that I think there is a lot of hypes about AGI, right? So if you go to media, people always say the AGI is coming, there is Q-star or GPT-5. I don't think that is the point. The point here is that with the current models that we have, the LLM is not stupid, right? So they are somewhat intelligent. In particular, like in this case, they understand basic form of causality. So they might not be able to come up with the Einstein theory of a general relativity, but it does understand the basic causality through actions. So what do I mean by that? So if your mom asks you to sweep the floor, and after you sweep the floor, you see the floor is clean, as a human, like you would learn that through my action, this has leads to a clean floor. And the LLM is able to do that, right? So this is what we show, even by not letting it to know like anything, just let it to play the SED like a feeding games, it would gain the knowledge as the human would. And this, of course, is a very interesting thing, because just like Ashley mentioned, you can talk about the interaction between the human and AI. So now you have the agent that can, with enough like compute, you can play the game infinitely, right? So you can play the AlphaZero infinitely. You will summarizes all your knowledges to your chess book. And you can also expect that maybe some of this summarized knowledge, even for a simple task, is more robust than the human, right? Just like how we play Go chess. But more importantly, of course, the human can examine the knowledge, because these are all in the form of natural languages, so you can check the knowledge. You can even include your knowledge, right? So you can put your knowledge as natural languages and impose the prior knowledge. But all this meaning that just like a very experienced researcher, you do not need to feed all the parameters, right? So if you are a very experienced researcher, especially for transients, so you know how to upward and downward stuff. And this means that you are saving a lot of compute, because you're using all these rules that you have learned to save the computational time. And why this is important? Because in principle, right? So as also like Ashley mentioned, we have a lot of sources, even without the transient. We have billions of sources on the sky, and 99.99% of them never get a study, because they're deemed too boring, too simple. But maybe there are lots of anomaly inside this 99.99% of the objects that never get studied by a student, because we never have enough a student to feed all the SED, right? But in principle, the AI can. In principle, the AI can fit as good as a human could. And this could be game changer, right? So for this like particular thing, meaning that all the data that we collected, we might be able to reason about that, just like a human would. Then we will be in what, like Salman said, we are back to the data stuff a regime because we have used up all the data. This, of course, is a very blue sky thought, right? So we show that this could work for SED, but even for SED, right, we have shown that this can only work with like a GPT-4 type of models. So you need to have a very capable models and still be able to run that fast enough and cost efficiently enough. And that is the problem. So how expensive is this thought process? So give you an example. So the SED like feeding that we have just shown typically costs about 100,000 token. You might ask, why so many tokens? Because there are many agents are working together and they need to discuss and come up with a new strategy. And those, because the LLM are not like super strong, this chit chat like between the agents are pretty long. And how much does that cost? If you take the GPT-4 models, it's about $10 per million tokens, meaning that this translate even for a simple like SED task, it will cost about $1 per source. You might say, well, like, is that a big deal? Yes, because if you take, say, the Euclid or Roman or even like LST, talking about billions of sources, right? So you're talking about billion sources. If each sources cost $1, then this costs $1 billion. So how much is $1 billion? $1 billion is like about the same build cost of this space telescope. So as you can imagine, if you go to your space telescope manager and say, hey, I want to double the cost to run the API, most likely he or she will not be thrilled, right? So meaning that we really need to cut down the cost by an order or two in order for this to be feasible. So what are the options here? How do we get there? So this is a third part that I want to quickly go through. So first of all, capitalism, yay, because there are lots of people are fighting for users. So there are lots of companies are building LLMs. But the question is that which one is good, right? So I think that's the problem. Like there are lots of interest in LLM for astronomy, but we never is able to benchmark that, like in terms of like astronomy, how strong these models are. So this is why with some of the people in Argonne, with Salmon groups, we are looking into some of these benchmark data set. We have curated a astronomy specific benchmark data set. I will not give you sort of the detail how we get there, but this is a typical like example. So this is asking why there is a number density drop for quasar at redshift of 5. It's a MCQ like question. You can think about this, the difficulty of this question are typical grad student like general exam like question. It's not that simple. Even for astronomers who are not working in that particular field, it might not be that simple for them. So with this benchmark, then we can start to compare the models. So what we are showing you here are the accuracy in terms of the MCQ, meaning that how many % of them get correct as a function of the cost, right? And the different line here is showing you roughly the trade-off of 10 times the worth of money. So if you look at this model, the GPT and Claude are equally strong, just that Claude costs slightly more and is slightly more accurate. But there are models like even the Google Gemini or the GLM. These are models that have shown to be very, very strong in the other benchmark. But for astronomy, they are not as good. In fact, they are orders of a magnitude not as good, meaning that if you use the Gemini, you are wasting 10 times the money. If you're using the GLM, then you are wasting about 100 times of the money for the same performance in this task. You can look at the cheaper version because just like the GPT have like GPT 3.5. All these models have sort of the cheaper version, but they just slide down the scale, right? So this line show that you can pay less, but then you don't get the performance that you want. So like as we have find that the GPT-4 is really necessary and non-negotiable, meaning that all these are weaker models, despite being cheaper, they are not the right thing to do. So this is bad, but you can ask, well, if you are in the position of, say, Salmon, you have the Argonne and National Labs, then you might have a lot of GPU, right? So you might not have a lot of money then, but in academia setting, it's much easier to ask for time in GPU than money, right? So how good the open source models are. So this is something that we also tested extensively, right? So like if you asked me 3 months ago, I would say that this is a no-go, right? Even 3 months ago, we are 10 to 20 points worse than like GPT-4. But things has changed, like especially this year, especially in the last 3 months. So if you now see some of the strongest models, like the Llama 3, the Q12, the biggest like Mixtro, they are almost as good as a GPT-4. And in fact, they are better than a Gemini and GLM for this task. So yay, right? So we can have open source models, but nay, because these open source models is only as strong as these closed source models, only at the 70 billion parameters. So what does that mean? Meaning that we are just trading off the insurmountable amount of cost to a insurmountable amount of GPU. Why? To give you an example, so if you run the Llama 3 70 billions, then it has a throughput of about 100 tokens per second for 4 GPU. This meaning that for one SED sources, you need to run the reasoning for about 15 A100 GPU minutes. It means that if you have a billion like sources from Euclid or Roman, then you will need to run about 10 million GPU days. If this seems too large to comprehend, meaning that even you give me a cluster of 1,000 GPU, like POSI, I still need to run POSI or NCI for 30 years, right? So nay, because the open source model seems good, but they are not scalable at this point, right? So this is why it leads to a lot of things they have been working on in the last 6 months, understanding can we fine-tune a large language models to do well in a specific task? Like, can we use a smaller like models? It's generally not as strong, but maybe it's good enough to do some of the tasks that we want for the agents. And this is why we started to work on this. That used to be called the TBD, and some of you might know, but the core group has moved on. So now it's called the AstroMLab. Who are they? So there are a bunch of people from the ADS, from Harvard. There are people from the Oak Ridge. There are also like people from the Argonne Lab that are working on that, with also the people at UIUC. So we have a lot of like support, including from NCI, from Gadi, from POSI, but also from the US, from a Frontier. And we spent a lot of time to learn this, right? So basically, we have not like released like many models, but most of the models that you have in mind, we have trained that with all the astronomy archive. But we didn't like release that because we find a very interesting thing, which is for the very strong models, right? If you look at the state of the art small models, like if you train them, then they become worse. Like it might seem to be a good idea to train them, but for most of you can see, it actually become worse because the models are quite brittle. You can stay the same if you have a bigger model, if you have a 70 billion parameters, and if you have the support from Frontier, you can fine-tune that and doing the continual pre-training, but it just leads to the same performance. So it's not making things worse, but it's not like improving. You can talk to me why this is the case. I think we have some theory why this is the case, but the point here is that this also seems to be not very scalable. Most of the LLM seems very brittle. Maybe we are doing something wrong. We would love to work with the industry like expert on that, but yet we have not seen any significant gain. Again, that despite a lot of interest, like a lot of talks, but most of them seems to be mostly just aspiration. Right. So what should we do? Right. So it seems like we have a very cool idea. We can reason about all the sources, but we are too poor to do that. So what should we do? I will start by quoting Warren Buffett. The trick is when there's nothing to do nothing. Or there's the reason to do nothing is because, as Warren Buffett say, the stock market will is designed to reward the people who are patient. Why this is the case? Because you have to trust Jason Huang, right? So the NVIDIA is growing. A lot of the company is doing like GPU. The GPU compute is exponentially increasing, meaning that the LLM is exponentially become cheaper and cheaper over time. But how fast, right? So how fast the price is doing. So the question the student might have is, should I do that now? I only have 3 years or 4 years for grad school. The answer is yes. So if you look at the benchmark that we have shown, like remember this line here, show you the price is dropping by a factor of 10. If you look at Claude, within 6 months from July last year to the March this year, it dropped by 100 times, meaning that for a given performance, the models that you are running now is in principle 100 times cheaper than 6 months ago, right? And this is also applied to all the company. And you might say, well, this might plateau because we are getting stronger. No, because Claude just dropped their latest model. So this is Claude 3.5 Sonnet. This is 3 months. Again, in 3 months, it's improving equivalently. The price is cheaper by 100 times. Meaning that even in the most conservative limit, the pricing e-folding time is about 3 months. So things that will cost you $1 billion today, in a year, will cost less than a postdoc, right? So that's the summary that I want to just like, of course, that this is more like blue sky, but I want to talk about, so what we have discussed today is that we try to quantify what is like going on in AI for astronomy. And the way that we did that is through the knowledge graph. I think that there is a loss of hype, but there's still a lack of innovation. And in particular, right, I think all the things that we are doing are great. I'm not saying that like all these are not great, but just that a lot of things we are still using AI as a tool instead of, as the Peter lesson say, we should create the type of thinking that could scale up to infinity. And the way that you can scale up to infinity is not focusing on individual tasks, but rather building up a methods like using LLM for for reasoning that could scale up. You can say the example that I show is very simple, sure, right? It's an SED like feeding. It's not that complex, but you really show that the LLM like agent even now have the ability to distill some of the basic causality. And that will change how astronomy is done, because you can done end-to-end like a research in astronomy. But of course, the problem now is just how to do that at scale and fast enough. But with the speed that we have been seeing, this like amazing speed that no one has seen in the history of the humankind, that either the performance and the dropping of the price of the prices, I just want to remind you that like not too long ago, there are very few people can have a cell phone, but we all have a cell phone in a few years, right? So, and this is, I think, what is perhaps one of the more exciting things that I believe that could happen in AI for astronomy. I will stop here and take any question that you might have.
That's great, Yuan-Sen. That was a really intriguing talk. So just looking at the Q&A tab, we've got no questions just yet. So I'd encourage the audience to either enter their question into the Q&A tab or to raise their hand. I was intrigued by this universe TBD. I've heard about that before, but don't know a lot about it. And I see it's turning into AstroMLab. Could you talk a little bit more about that and maybe how people could get engaged if they're interested?
Right. So I think the UTBD is still there. I think just the mission has split a little bit. So used to be there is the community like a building part, but there's also the model like training part. So the AstroMLab is focusing on the training of the models, right? So more like the sciencey part. So this is why we thought we want to be like move fast with a small group. People can engage, right? Like people can reach out to me, like if you want. There are lots of it's great to have more people to be excited about this idea. Not even just doing research, just understanding how to build a agentic like research, right? How to build an end-to-end like pipeline for some of the tasks that you need to like repeat like many times. And most of them, like if that part cannot be done with a simple optimization, then yeah. So we really encourage people to do that. Like it would even be great to have some form of like workshop, to just brainstorm.
Still waiting for questions. But one thing struck me as well when you were talking about the large language models and ChatGPT and the like. And you talked about working with those companies, or to what extent can you work with those companies? Is there enough in there for them to want to invest in astronomical research?
Yes and no. So we did talk to a few company. There are places that are more like receptive, but the challenges here is that the investment that we have, like especially for individual group, is too small to entice them. Even you say, we can do this for my project for 100, 1,000, or even like a small grant, most likely they would think it's too small, right? But if you say we have like SKA like data, or we have like Euclid or Roman, so this will be more bigger scale, and this is the part where I think the management will play a big role, because like this is beyond individual researcher like ourselves in AstroMLab that can change, but it requires the management to realize that this is a path. Yes, we are asking maybe now like 100 like millions, but it's a path that is worth like doing.
Yeah. Okay. Yeah. We've got some questions now. So Min Hyun said, "Great talk, Yuan-Sen. Astronomy data is getting very big, as you said. For our work, is the contextual or token limit an issue now? And can you comment on the potential for larger token models for astronomical discovery?"
Yeah, so the thing is, it really tied to, so it depends on what task you are doing, right? So for the different like agent, why we break that into like different agents, because some of that require longer context windows. Like if you want to like retrieve like information and like propose new action, then you need a long contextual like windows. But in many cases, it's not really that limited by the context windows. It's really about the strength of the LLM. So the current limit, why we need so many tokens, is really like individually the LLM is not like very strong. It's just that you have a bunch of younger students, and how do you make best use of them, right? So you need to break tasks into like the really like less specific tasks. Of course, if you reach to AGI, then no problem. You just say fit the SED and reason about the SED, right? And that is why humans are still has an edge, because we have a very effective way. But the fun thing about what we have shown is that yes, the LLM is not like very strong, but you can help them. You can let them to remember what works. Just like, okay, your native thing, yeah. So that's the point.
Okay. Any more questions for Yuan-Sen? As I said before as well, you can raise your hand. Oh, there's a question in the chat actually. So Humin Chu asks, do you believe AI can do science, for example? There's symbolic regression to guess the physics relations for different variables by learning from the data. Do you think AI is doing science here? And what's the difference between this mode and the mode you mentioned in the talk?
Right. So I guess this depends on your prior belief of what is the fundamental causality structure. My own belief, which is also like restricted to my own belief, is the knowledge that we have in astronomy are quite often more fuzzy than a symbolic. It's a part of the thing that we should aim for, but I don't think it is a very big set of the causality that we care about.
Okay. Any more questions for Yuan-Sen? If not, well, if you do have any questions that strike you before the end of this showcase, you can maybe raise them during the panel discussion, which we'll have at the very end. But yeah, so I'd like to thank Yuan-Sen again for that really great talk.